So number 6 says, how long will it take for 7,000 to grow to 25,200 at an interest rate of 10%? If the interest is compounded quarterly, round the number of years to the nearest hundredth. Okay, so how long for 7,000, so I'm going to write down 7,000, to grow to 25,200, that's a lot of money, 10% interest compounded quarterly. Okay, so let's look at our data and let's look at our equation. So we're going to use, this is the compounding equation, not the compounding continuously, but the compounding quarterly, or in any time increments other than continuously, is going to be amount after time is equal to amount that you start with, that's the wrong one, 1 plus r divided by n to the nt. So this is the formula that we're going to use for compounded quarterly. We're going to use n is 4 because that's 4 times a year. So we're going to erase the n's and put in a 4. We're going to erase the r and put in 10%, which will be a 0.1. We're going to erase the a sub 0 and put in the 7,000. And we're going to erase the amount after time and put in 25,200. Okay, so we've got all of our data in the correct spot, and we can do a little bit of cleaning up before we finish. So we're going to do a couple of things here. We're going to divide this side by 7,000, and we're going to divide this side by 7,000, okay, which is going to cancel this completely. And then I've got 1 plus 0.1 divided by 4. So on my little calculator, I'm going to do 0.1 divided by 4, and then I'm going to add that to 1, and I get 1.025. So this will be 1.025 raised to the 4t. Okay, so let's clean all of that up on a new board. And we're going to have, I'm going to go ahead and just do the math on 25200 divided by 7,000. And I get 3.6. So 3.6 is equal to 1.025 raised to the 4t. Okay, so that's what we had before, and it cleans up very nicely to this. So now I have a base and my exponent is over there, so I'm going to take a log of both sides. And in this one, there's no reason to take a log base e, so I'm just going to take a log base 10 and use common logs on this one. So I'm going to get log of 3.6, and that's log base 10, is log base 10 of 1.025 to the 4t. But we know that once we take the log of both sides, then we can take this 4t and it can run around as a coefficient, and we'll get 4t log 1.025. Okay, and then on the other side, log 3.6. Okay, so now I'm going to, now that I have gotten the exponent has come around here, now my variable is out front. So can I divide both sides by log of 1.025 and divide this side by log of 1.025. Okay, so now I am almost there because I've got this goes away and I've got 4t is equal to all of this. So now all I have to do is calculate this, divide it by 4, and I get the t. So there's the board that I have at this time. So now I'm going to finish that math, and we're going to divide log of 3.6 on the calculator, and I'm going to divide that by log of 1.025. So I did that math. Okay, I divided, and now we're going to take that and divide it by 4, because we have that set equal to 4t. So we divide that by 4, and we get 12.97. Okay, 12.97 years, and that is the correct answer. So when we're trying to do one of these compounding interest problems, we're going to end up needing to take the log of both sides to separate the exponent from the base. And so that is how number 6 is done. So now we're going to move on to number 7. And number 7 says the number of acres in a landfill is given by the function b is equal to 3,900 e to the negative 0.05t, where t is measured in years. Remember, you have all these problems on the back of your PowerPoint, so I'm just reading them to you. How many acres will the landfill have after 9 years? So they're giving us the equation, and all we're having to do is plug in the 9 years. So we have b is equal to 3,900 e to the negative 0.05t, and then it tells us to plug in 9 years. So I'm going to take the t out and put a parenthesis and put a 9. So this is basically just a calculator problem that we're going to plug in. But the biggest thing about this is to correctly use your order of operations. So I'm going to take my exponent up here, and I'm going to multiply that out. 9 times 0.05 would be 0.45, and then I've got an e to the negative 0.45. So I'm going to do that on the calculator and get, remember my e is on my natural log key, so I'm going to have e to the negative 0.05 times 9, because I forgot to just put 0.45, so we'll just do it that way. So I should get that, and now I've got to take that result and multiply it by 3,900, so times 3,900. Always do your e part first, your exponent part first, and I get 2,486.74 acres, 75 acres, and they rounded that in the answer key to 2,487 acres. Okay, so that one was number 7, and now we're going to do number 9. Okay, you're going to jump over to number 9 because a lot of these are pretty similar, and I don't want to take all night. So we're going to jump over to number 9, and it says, in a town whose population is 3,000, okay, a disease creates an epidemic. The number n of people infected t days after the disease has begun is given by the function n of t is 3,000 divided by 1 plus 15.2 e to the negative 0.6t. Find the number infected after 12 days. Okay, so we're glad that this is a limiting function. In other words, you can't just keep on getting infected. This is one of the functions that has the a limiting factor here. So basically that limiting factor is the whole population, though, so that's kind of scary. It's limited by the whole population. I guess the whole population could get infected. So this is after 12 days. So we're going to put a t is 12. So we're going to take out the t and put in the 12 there. And then again, this is simply a calculator problem, learning how to get the calculator the order of operations correct on these. So I'm going to start down here with my exponent. Okay, so I'm going to do e to the negative 0.6 times 12. And that's going to wind up being second. The natural log button is my E button. And then I'm going to do negative. Now, when you're doing negative on your exponent, always use this key down there. Okay, negative 0.6 times 12. Close my parentheses. So there's my exponent onto my E there. And so I'm going to hit enter. And then I'm going to multiply that by 15.2. So times 15.2. And then I'm going to add 1 to that. Okay, so now this is the number that's on the denominator. Okay, so that's what I'm going to divide by. And I'm going to put that in the denominator by using this key right here. If I use this x to the negative 1 key, it will take what I have in the calculator and put it downstairs. So I'm going to put answer negative 1, and it's going to go downstairs, and then I'm going to multiply by 3,000. Wow. Okay, that's a lot of people getting infected. Out of a 3,000 person town, 2,966 people get infected in 12 days. That's pretty scary. Okay, so that is the correct answer. 2,966 people would be infected. All right, so let's do a Newton's cooling law problem. This is number 11. Okay, and it says, Newton's law of cooling states that if a body with temperature T1 is placed in surroundings with temperature T0 different from T1, then the body will either cool or warm to temperature T of T after time T in minutes, where T of T, now we got the equation, T after time T is equal to T sub 0 plus T sub 1 minus T sub 0, or the difference between the two, e to the negative k T. Okay, so the negative k is showing that this is a decaying function. The temperature is going to decrease because it's out cooling. Okay, so a dish of lasagna, there's your equation, a dish of lasagna baked at 375 degrees Fahrenheit. So 375 is the temperature that is baked at, is taken out of the oven into a kitchen that is 69 degrees Fahrenheit. Okay, after 6 minutes, the temperature of the lasagna is 318.5 degrees Fahrenheit. So 6 minutes, it is 318.5 degrees. Okay, what will be its temperature 12 minutes after it's taken out of the oven? Okay, so we're going to say 12 minutes to the nearest degree. Okay, so we have to find out what the answer to this is. And so we're going to take this data, and remember, it's if a body with temperature T1 is placed in surroundings of temperature T0. So our temperature that it's taken out of the oven is our T1, and then it's put in surroundings that are T sub 0. Okay, so that's where we're going to substitute each one of these things into this cooling function. All right, so we're going to say T of T is, and then T sub 0 is 69 plus, and then we're going to have T sub 1, which is 375 minus the 69 in the parentheses, e to the negative k T. Okay, so there's our function with our data in there, and now we have to put in our 6 minutes. So we're going to put in our 6 minutes, which is our initial piece of information they give us, and they also give us how cool it was after 6 minutes. So that's our temperature after time t was 318.5. Okay, now that allows us to find our K. So we're going to be able to find the rate at which it is decaying or getting colder in this case. And so K is the only thing that's not known, notice. So we're going to start to work through this. And the first thing we're going to do is find the difference between 375 and 69. And we're going to get 375 minus 69 is 306. So this is 306 times e to the negative 6k plus 69 is 318.5. So in my order of operations, the next thing I would do is I would get this 69 and subtract it from both sides. So we're going to subtract a 69 and subtract a 69. So now we've got 318.5 minus 69 is 249.5. Okay, is 306 e to the negative 6k. Okay, so there's our equation now. And we're now going to divide by 306 on both sides. So we're going to divide by 306 to get the e by itself over there and divide by 306. So this is going to go away and we're going to get 249.5 divided by 306 is 0.815. So we get 0.815, and I like 4 digits, so I'll put a 4 next because it's rounded. Okay, so 0.8154 is e to the negative 6k. So that's what we have so far. So we're going to get another board here. And now we're ready to take the natural log of both sides. Okay, so we're going to take on the left the natural log of 0.8154, and I'm using the natural log because I have an e in this problem, is equal to the natural log of e to the negative 6k. Okay, so once I get my e here separated out, then I am ready to take the natural log of both sides, which I did there. Now, my exponent is going to run around and become a coefficient, so I get negative 6k natural log of e equals natural log of 0.8154. So now the natural log of e goes to 1, and I can divide this side by negative 6 and divide this side by negative 6. Now, what do we know? Let's think about this for a minute. The natural log of 0.8154, what do you expect that number to be? I expect that number to be negative, not because I'm dividing by negative 6, but because any log that is between 0 and 1 is going to be negative. Remember that graph that I showed you? Here's my anchor point for a logarithm, and it's going to go whoop, like that. So in between 0 and 1 on the x-axis, the y goes down and is negative. So we're going to have a negative divided by negative is a positive number, but notice that my equation has got a negative built into it. Okay, so we're going to divide these up. So natural log of 0.8154, and that's going to give me a negative 0.20407, and then I'm going to take that and divide it by negative 6, and I get that k is equal to 0.0340. 0.0340. Okay, now they tell me to find, what I'm trying to find in this problem is what will its temperature be after 12 minutes. All I've done is find the K. I found the constant of cooling. So now I have to take this K, put it back into the original problem, and go back and set up what the original problem is. So I'm going to go back to the very beginning, get a clean board, and remember my function was t after time is t sub 0 plus t sub 1 minus t sub 0 e to the negative kt. Okay, so now it's asking me to write what is it going to be after 12 minutes. Okay, so we're going to say it came out at the same, 375. It is into a room that is 69. So a lot of this is going to be the same. So we're going to say T in 12 minutes, okay, is going to, they're saying what will the temperature be? So that's what we don't know. T of 12, we'll go ahead and put a 12 there, is T sub 0, which is the temperature of the room. So that was our 69, okay, and we've got that up there at the top of this board. That was the equation that we had, but we're not going to keep some of this in there. We're going to start back afresh, plus the 375 minus 69, which was in parentheses. And then now we know what our K is. So we're going to say e to the negative 6k, negative 6k, and the K, remember, where K is 0.0346. Okay, so I didn't have room to write all that, so I just wrote a negative 6k, and then where K is 0.0346. So now I'm going to start calculating this out. So negative, oops, it's not 6 anymore. Now it's negative 12. I'm sorry, I'm going to go up there, negative KT, not, I looked on the wrong board. So it's negative 12T. Because now we're doing 12 hours, not 6 hours. Okay, I was looking on the wrong board. So now we're going to do all the math again. And when I subtract this, I still get 306 here. So I get 69 plus 306. And I'm going to multiply that times e to the negative 12 times 0.0346. So now this is going to be the new temperature here. So we're going to start doing the calculations. So 0.034, I'm going to do e to the second natural log. Okay, so we're going to do e to the negative 12 times 0.0346, close my parenthesis, enter. Okay, so that looks right to me. So I put that in my calculator because I'm trying to work on this. Okay, so now I've got the e part. So now I'm going to multiply that by the 306. So times 306. And then I'm going to add that to the 69. So add that to the 69. Okay. And we have the same answer they do, which is 272. I actually got 271.02. So I'm not sure why they got 272, but let me see what they said about rounding it. They said round it to the nearest degree. Okay, so the discrepancy can happen because I'm keeping 4 decimal places and they are probably not keeping 4 decimal places when they do those calculations. And this is why I suggest that you do the 4 decimal places, because it very quickly will make a difference of a degree here. So basically that's probably a rounding error, and mine's probably more accurate, so I'm going to go with it. But they said 272, I say 271, but I like to keep my accuracy as far as I can, because the exponential is going to change quite a bit with every little change in the exponent. So I like to keep that going. So let me show you your board so you have a chance here to look at this. So this one was the first board here, number 11. Okay, so that was the first board that we did. And then we plugged it into this here. We started plugging in all of the information there. Okay, and then we ended up finding out, we took the natural log of both sides, found out what our K was. And then finally, after we find out what the K is, we can go back and find how much it will cool after 12 minutes. That was a long problem. All right, so we're going to do number 13 on the back of the PowerPoint questions. And it says, which of these is larger? So we've pi to the 1.3 and pi to the 2.4. And because the base is the same, and because the base is greater than 1, we are able to say without a doubt that 2.4 is going to be greater than, pi to the 2.4 is going to be greater than pi to the 1.3, because we're taking a larger number and raising it to a bigger power. Okay, so we have to be careful. This is only true when the base is larger. So if I just took, instead of a pi, I took a 3 to the 2 and a 3 to the 1, just to make it a little bit easier, because pi is very close to 3, and 2.4 is close to 2, and 1.3 is close to 1. So I'm taking the same base. This is going to be 9. This is going to be 3. So this one is going to be bigger, right? Because it's the same base. The base is greater than 1. But what if I took 1/2 and I squared it, and I took 1/2 and I raised it to the first power? Now, the one that's the biggest is 1/2, because this is going to be 1/2 times 1/2, which is 1/4. And that's cut in half from what it was. So basically, every time we multiply by bigger power, we cut it in half again, and we're getting half the value. So when the base is less than 1, then a power will actually decrease the value of the fraction. Okay, so now we're going to look at number 14, and number 14 is very interesting. It says, suppose that $1,000 is invested for 5 years at 4% interest, compounded annually. In what year will the most interest be earned, and why? Okay, so here is our basic equation. Here is our compounding formula there, compounded interest. And since it is only one time a year, compounded annually, we put a 1 here and a 1 there. So this is just not simple interest, but it's only being accrued once a year. So we're going to use this formula. And then what I did is I went ahead and just said, okay, I'm going to go ahead and plug it in. Of course, it makes sense that it's going to be year 5, because every time we compound, we're putting more money back in the principal. And the longer it compounds, then the more you have to work with, which means that you're going to be accruing interest on a larger amount of money. So, and that's basically what the answer said. But I went ahead just for fun, and I figured out the amount that was in the new amount every year. And then, so to find out the interest, I could subtract these 2 years and find out what the interest was every year. So what I found was this. This is the interest function, is just, okay, the first year you get interest at the end of the year, but basically taking the difference, I had the most interest at the very end. So the 5th year is going to have the most interest because I'm just subtracting the value at the end of the 5th year from the value at the end of the 4th year. And each time I do that, notice that the interest is increasing because the account is building. So even though I have the same amount of interest rate, the principal is growing every year. So it makes sense that it will be the 5th year, and it is. Okay, so now I'm going to look at number 15, and it says explain how the equation log x is 1 could be solved using the graph of f of x is log x. Okay, so basically log base 10 of x is 1. We can use what we know about logarithms, but they don't want us to. They want us to use this function to solve this problem. So basically, I'm not going to do what I normally would do. What the fastest thing is to realize this is a base 10 and say, well, 10 raised to the 1 power is x, so x must be 10. Okay, that would be using the knowledge of the logarithm to solve it, but they want me to use this function. So what I'm going to do is I'm going to graph it, and I'm going to plug in log of x into y1. Okay, so I'll plug log of x into y1 because they told me they wanted me to use this function. And then I'm going to plug into y2, I'm going to plug in the number 1. Okay, so I'm going to plug in a 1, and so I'm plugging in the left-hand side in y1 and the right-hand side in y2. I'm going to graph the two of them, and then I'm going to find their intersection. So that's what we're going to do. We're going to plug into our graphing calculator. On the left, we're going to do y1, and we're going to have to clear out that old stuff in both of those. And then on y1, we're going to put log of x. So log x. And then in y2, we're going to put just the number 1. Okay, so now I've got log x under the first y and just the number 1 under the second y2. Okay, so now we're going to graph, and the intersection is actually outside my window. So I'm going to close my window in a little bit. No wonder. My window is only going from x min of -5 to x max of 5. So I need to adjust this window. I'm going to at least put in my standard window of -10 to 10, and then -10 to 10 again. So we got back to our standard window, and now when we graph it, it's going to be a little bit more able to be seen. Okay, so we've got our line across the top. So now I'm going to do an intersection of the functions. So I'm going to say second, calculate, and I'm going to go down to the intersection of the two functions. It says, please put your cursor on the first curve. So I'm going to put it on the logarithmic curve. And then it says, check on the second curve. So now I've got it on the line. And it says, do you want me to guess? And I said, please guess. And it's going to tell me that the intersection is at 10, 1. Which is exactly what I knew, but now I can do it with, so basically the answer they gave was graph them both on the same set of axes and then find the point of intersection, which we did. Okay, so hopefully you're getting used to using your calculator to help you solve problems. Okay, so the last one that we're going to do on this problem set is we're going to find the error in the following. So we have log base 3 of 2 plus log base 3 of m is log base 3 of 2 plus m. Okay, so I can see the problem right away is when we have the sum of the logs. Let me write this a little better. Log base 3 of 2 plus m. Okay, so shouldn't this right here be a times? Because when we have the log of the product, then it's equal to the sum of the individual logs, not the sum. Okay, so remember the rule is log of m times n is equal to the log of m plus the log of n. So that is the property that they're trying to get you. So they've got a little plus in here, and it should be a times. And we have thoroughly gone over the word problems and the concepts in 5.6. So I declare you ready for your test, whether you have it tomorrow or the next day. Hopefully you will take the time to thoroughly do your homework online, to listen to your videos, work through problems in the back of the book. Remember, you just can't be too prepared for this last test and the final exam. So study hard, and this is Mrs. A, and may God bless your day.